in this lesson, we'll continue our study of subatomic structure. We're going to look at those orbital notations and electron configurations that we learned about in previous lessons and learn to write the formulas for monoatomic ions using those. Then we're going to also learn how to write Lewis dot formulas. Actually, we're going to learn what we're going to call electron dot formulas, which will later become Lewis dot formulas and Lewis formulas. But for now, we're going to learn the electron dot formulas and learn to also write ionic formulas from those. So in our last lesson, when we were looking at how to write electron configurations, and I showed you how to make these shorthand or noble gas electron configurations, we ended up with only those electrons in the highest energy level sort of showing here. Okay? Now some electron configurations, when you do the shorthand, have a D sublevel showing here. All right? And that's important for electron configurations, but for writing initially at least orbital notation, electron dot formulas, we're going to kind of ignore what's in the D sublevels if they're there at all. Okay? The D sublevel is sometimes involved in chemical reactions, but we don't get into them a lot in high school chemistry at this level. There is one case where I'll show you one that you're not really responsible for, but I want to show it to you a little later in another unit because you'll see it later in college. But for us, all we care about are those electrons. When we're doing electron dots, those electrons that are in the highest primary energy level. When we're looking at electron dots or electron dot formulas, we're only looking at those electrons and care about those electrons that are in the highest primary energy level. And those electrons have a name. They're called the valence electrons. The electrons at the highest primary energy level are the ones that are going to be used in electron dot formulas, and those are called valence electrons. Okay? You need to know that term, valence electrons. So let's look at this one. Since this is the one that I first used yesterday to first show you how, or in the last lesson, to first show you how to do the shorthand or noble gas configuration. Let's look at the number of electrons here in this highest primary level. So how many electrons are there in the highest primary energy level? Huh? How many electrons in the highest primary energy level? 8. Say it again. 8. Count them. That's the highest primary energy level. 3. How many electrons are in there? 8. 2 and 6. 8. Okay? Well, the highest primary, the primary energy levels are the stuff you learned in physical science. You know, these things are in the concentric rings. Okay? But when you're building up to get a an electron configuration or orbital notation, there at any one time can only be only 8 electrons in the highest energy level, and that's because when you get to the D sublevels, you have to drop back one level to put electrons in the D sublevels, and you don't know this because we don't do it, but we drop back 2 levels to put in the F sublevel electrons. So at the highest energy level will have a maximum of 8 electrons. Okay? Please remember, the highest energy level has a maximum of 8 electrons. Okay? At any time. The reason I emphasize that is because on every test, I'll ask somebody for something like give me the electron dot formula, and they'll give me this with 32 electrons or 16 or 18 electrons or something. And what's the highest number of electrons you can have in the outermost or valence level? 8. So just try to remember that, okay? It's really important that you know that. So for argon then, we need to put 8 dots. This is called an electron dot formula. The dots symbolize electrons. So what we're going to do is just going to write the symbol for argon here. And I want you to imagine that there is a box around this, okay? You don't have to draw the box, but I'm just going to lightly draw in a square around this. But when you actually write the electron dot formulas, there is no square, okay? I'm just doing it to help you understand where the dots go. So what we're going to do to get to 8 dots is we're going to put 1 dot on each of the 4 sides, or as many dots as we need. Okay, so if you have only 2 dots, you'll stop at 2. If you need 3 dots, you'll stop at 3. But this time we're going to need 8. Okay, so 1, 2, 3, 4. Once I've got 1 dot on each of the 4 sides, then I can pair them up. 5, 6, 7, 8. And that's an electron dot formula for argon. Does that seem hard? I hope not. Well, let's do another one, and then I'll let you practice a few, okay? So all this stuff is tied together, okay? Everything we're looking at here is very similar in form. We're just kind of building up in our understanding of these things. We started with orbital notation, and then we're building up. So let's look at the orbital notation. Let's say for aluminum here. You have this in your notes. I hope you have that in your notes. You know where to find it. How many electrons in the highest primary energy level are there for aluminum? Did I say that right? How many electrons are there in the highest primary energy level of aluminum?
1. 3.
Well, you can't just count this one because this 3 is also the highest energy level. 3. Okay? I'm trying to get you to think about that, okay? It's not just the most recent P sublevel or D sublevel. It's whatever the highest primary energy level is. This 3 here tells you that's the highest primary energy level. Does that make sense? All right. So that's 1, 2, 3 electrons. So for aluminum then, we're just going to take 1, 2, 3 and stop there. Okay? All right. Now, if those 3 are there, then what I was going to say is you can put them on any 3 sides you want to. You don't have to use that formula. You can use this formula, okay? Or you can do this. All right, you can have it on any 3 sides you want to. All right, you can't 4. You're right. Okay, I meant to do the 3 top ones. I'm so used to doing on order there. I kind of skipped over that. So, okay, so any of those are fine. You can only have 8. 8's the maximum number you can have, because all the D and F sublevels are back a level, or in the case of F, it's back 2 levels, and we don't deal with that in this class. Okay? You can't have any more than 8. Now listen, that's an important thing though, because no matter what I do, and how often I say it, and how much I plead with students, somebody's going to put 18 electrons around some atom. Okay? When you do electron dots, 8 is the maximum you can have. Okay? You got to know how to figure out how to get those 8 though. All right? You got that? No? You don't got that? Well, let's do another one then. How about let's choose one of the elements then we did yesterday where we have to skip over the D sublevel. Let's do electron dot notation for germanium. Okay? No, we didn't do it. We're going to look at it now. All right, so in germanium, we're only interested in those electrons that are in their highest primary energy level. So we're only interested in those that are represented by these elements right here. Remember, it's not the elements that have the electrons. They're representing adding of electrons to the electron cloud, okay, in a ground state. And so in the highest primary level, 4, because this is row 1, 2, 3, 4, I have 2 electrons in S, represented by the position of potassium and calcium. And in 4, these electrons, all 10 of these, drop back a level. These are in 3. We don't care about those. Not for this anyway. We do care about them, but just not for electron dots right now. And so these 2 electrons, represented by the position of gallium and germanium, are in the P sublevel, but what primary level are they in? 4. In the P sublevel, in a P orbital, or in P orbitals, 2 of them, but they are in the 4th primary level. It's the 4th primary level of electrons we care about, because that, for germanium, is the valence level, the outermost level. Okay? So we just draw the symbol for germanium. We put 4 dots. 1 on each of the 4 sides, and we stop because we only need 4, right?
So, did you say that there can't be any more than 8 in one of those things?
That's right.
Okay. But how did you only get 4? Yes, I bet like 2 for each.
1, 2, 3, 4. It's only the highest level electrons we care about. 1, 2, 3, 4. Only the highest level electrons we care about. Okay?
The highest level of each
All right, here's what we're going to do.
region of that row.
Yeah, here's what we're going to do. We're going to start, I'm going to give you guys a number. Okay? Let's, what? I don't know. Let's see. You're 3.
I'll be 14, that's my number.
You're 4, 5, 6, 7. You okay, Lauren? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Got it? That's your element number. I want you to find your element on the periodic table and write an electron dot formula for it. Electron dots. Okay, so what we're going to do here is we're going to take silicon. I'm going to draw out the complete orbital notation and complete both kinds of electron configuration and use that to figure out how many electron dots we need. If you're struggling figuring out how to get how many electron dots, you can always go back and do this. Now, if you choose not to use up some pencil graphite and just sort of guess, well, that's your grade. I want you to pass. I want you to make an A, but I can only, like the old proverb, you can lead a horse to water, but you can't make them drink, right? All right?
Oh, I didn't know that one.
You didn't know that one?
No.
Okay, that's an old, farming proverb or whatever. All right. So here's the orbital notation for silicon. Got all the electrons in 1s. Got all the electrons in 2s. All the electrons in 2p. And then 3s is full. And then in 3d, we have 2 more electrons we need. Once you start putting any electrons into a d sublevel, you have all 3 orbitals there, even though some of the orbitals or one or more orbitals are empty. So in 3p then, we've got 2 electrons, and you put 1 in each box, and you don't pair anything up because you only got 2. Okay? So if I count the number of electrons in the highest primary energy level, I can tell how many electron dots I'm going to need. Okay? And the highest energy level includes anything in 3. Okay? So it includes 3s and 3p. And so all these electrons here and all these electrons up here are part of the highest energy level. So I have 4 electrons. Okay? So from this, I can figure out that silicon's initial electron dot formula, ground state electron dot formula, will have 4 electron dots. 1, 2, 3, 4. Okay? Now let's do the electron configuration then. Silicon 1s2, 2s2, 2p6, 3s2, 3p2. Okay? I've got 2 electrons here in 3s because 3 is the highest energy level. I want all of these electrons and all of these electrons. So again, I've got this electron dot formula. And the shorthand version of silicon's electron configuration, I want to use neon as the kernel. And I got 3s2 and 3p2. Again, 4 dots because I got 4 electrons in the highest energy level. Now, just so that we don't leave everybody confused here at all, let's jump down to, let's say, arsenic, which is down 1 and over 1. And I'm just going to do the shorthand configuration here for that and show you something about the D sublevels. So here's arsenic. The next lowest noble gas is argon. And then we've got 3s2. I'm sorry, that's 4s2. I apologize. 4s2, because argon's in the 4th primary level. And then we got 3d10 and 4p3. Okay? only the electrons in the highest energy level are going to be part of our electron dot formula. So that's only these electrons here and these electrons here, because 3 is in a lower energy level. So when we write the electron dot formula for arsenic, we need 5 dots. 1, 2, 3, 4. And somebody asked me this a moment ago, yes, you can choose any one of the 4 sides to put that last dot on. In fact, there's nothing special. I usually always start at the top dots, but you can start on any one of the 4 sides. It doesn't matter. Okay? So I'm going to put my extra dot over here just because I chose to. Okay? Got that? Now, somebody up here wrote their electrons on the right-hand side in double-barrel shotgun form. Okay? When it's on the side, you should write it in over and under shotgun form. All right? Y'all don't know what an over and under shotgun is, do you? Yeah. So a double-barrel shotgun has 2 barrels that side by side. Over and under has the barrels that go like this. Okay? All right. I just thought, you know, here being in the South, and everybody likes to go hunting around here. You know, y'all know what that is? I'm saying. Okay. So, well, I wouldn't say that's wrong, because right now we're just beginning anyway. But the correct way to write this, then, if you want to put your dots on the top here and on the side, would be like this. Okay? But now, this is okay, and so is this, and so is this. Okay? Any of those are fine. All right? Just, you can't, yeah, you just, when it's on the side, it's got to be over and under. When it's on the top or bottom, it's got to be side by side. All right, so here is the orbital notation for sulfur and the electron dot formula I wrote from that. Okay? Now, sulfur has 2, 4, 5, 6 electrons in its highest primary energy level. Both the S and P sublevels in 3 make up the highest primary energy level. It wants to have 8 because most atoms tend to like to have 8 electrons. Okay? So what's the easiest thing to do? Take away 6 or add 2 electrons?
Take away 6.
Really? Take away 6?
Add 2.
2 is smaller than 6?
Brady.
I mean, it's not a football game. We're not trying to, you know, run up the score here. Just saying. All right. So we'll add 2 electrons. You got that? See what I did? Now, sulfur had 16 protons and 16 electrons when it was just an atom. Now it has 2 extra electrons. What's its charge? Actually 2 negative, but negative 2 is what you would probably say. 2 negative because of the charge and not a negative number. Okay? So we're going to put a 2 negative here. Okay? All right, now over here with the electron dot formula, we need to add 2 extra dots. Okay? And we need a 2 negative charge because I have 2 extra electrons. However, to avoid confusion, when I put a 2 negative out here about what that 2 negative applies to. So if I put them there, you might think, well, that just applies to these 2 electrons up here. That's not what I mean. To show that 2 negative applies to the entire sulfide ion, we're going to put a bracket around it. And by the way, when you have a monoatomic ion that's negative, it's called, you change the ending of the name to "ide." So sulfur becomes sulfide. Only applies to negative ones, not positive ones. Okay? Let's put the brackets around it when you're adding extra electrons so that you can show the 2 negative applies to everything and not just where the electrons are. Yes? Yes. Okay, all right. Now, we had 4 electrons, I'm sorry, was that right? Yeah, 4 electrons in the 3p sublevel, but I'm adding 2 electrons to 3p sublevel, right? So it needs to have 2 more, and that's going to be 6 electrons over here, which means I'm adding 2 electrons here. Either way, I'm adding 2 electrons, so that's a 2 negative here, and a 2 negative here. Okay, and down here, instead of 4 electrons in 3p, I'm adding 2 more, making it 6. A total of 8 electrons in the valence level now, because they want to have 8. That means this sulfur now has a 2 negative charge. We now call it a sulfide. And this is 2 electrons here and a 2 negative, and we get a sulfide.